Hello and welcome to another episode of Mr. Walker's Chemistry. We're going to start our bonding unit, so we're going to start talking about bonding in chemistry. And by bonding, I mean we're taking atoms and sticking them together in different ways. We're going to start off this series with a quick review of some major chemistry concepts, and then we're going to cover ionic bonding and ionic nomenclature. Alright, so the first thing is, what is the purpose of all this? So atoms of most elements are known to bond to other atoms. So how do they bond, and what forces cause them to bond? Alright, so that's our first big question, is basically how and why do they bond? Second question is, once they're bonded, how do you communicate this to others? How do you tell others that you've created a bond and thus created some new chemical? It's no longer just iron and oxygen. It's now something different. So what do we call that, and how do we communicate it? So let's review some stuff. First, what is an ion? All right. So make sure that we're up to date on what an ion is. All right. Remember that an ion is an electrically charged atom, meaning the atom itself has an unequal number of protons and electrons. For example, if we have a oxygen with a -2 charge, that's an ion, and we have 2 more electrons than we have protons. So how does the electrons alter the charge of an atom? All right, more electrons gives you a negative charge, fewer electrons gives you a positive charge. All right, so this should all be reviewed for you. When a positive and a negative get close together, so think about a positive magnet and a negative magnet, what happens? All right, they should attract, okay? So these guys are going to come and stick together, all right? So how do we know if an atom will become positive or negative? Well, that's a tricky question, all right? How do we know if it will gain electrons or lose electrons? And we learned this with the periodic table. So we have to look at the electronegativity. Remember, electronegativity is the ability of an atom to steal an electron. It's the want of an electron. So the higher the electronegativity number, the better a thief the atom is. All right. So remember fluorine, okay? Fluorine is the very first halogen. It's the smallest halogen. So it has a very high electronegativity because all it needs to do is steal 1 electron and it becomes quote unquote happy. It has a full valence shell of 8 electrons. All right. So fluorine has the highest electronegativity of 4. Francium has the lowest electronegativity of 0.8. And when we look at a trend, all right, or we look at a periodic table like this, we can see that. All right, so atoms over here do not really want electrons. Think about why, okay? And over here, they really want electrons, okay? And also think about why. Now notice that there are no noble gases because the noble gases do not want electrons at all. They're happy. They have 8 valence electrons. Okay, so why do you think the trend exists? This is what I've been asking in the last couple of slides. Why? Okay, you need to know why. Really understand it. So I've given you a couple of tips here. All right, the further an electron is from the protons, the harder it is for the protons to hold on to the electrons, and happiness has a lot to do with it. All right, so if you are not sure, if you cannot answer this question in 1 or 2 sentences, go ahead and pause, go back and rewatch. All right, rewatch the video on periodic trends, or look in your textbook in that chapter, okay? So, how is this electronegativity trend applicable? Well, in chemistry, we use it to predict reactions. All right, reactions occur when you move electrons. In other words, we're going to create or destroy a bond, which is what we're about to learn about. So we have to think about things like, will calcium and oxygen react? Think about their electronegativities and what charges they might get. Because remember, all atoms are trying to be happy. All right, so let's look at this. All right. In biology, for those of you who prefer biology over chemistry, we breathe oxygen. Okay, that's what we're really after. The rest of the stuff that's in the air, we don't need. We don't care for it. So when you undergo cellular respiration, you're breaking down glucose or sugar to get the energy. But where exactly does that energy come from? Well, it comes from the electrons that were excited by the sun in photosynthesis. So remember, flame test lab, right? You can excite electrons by putting energy into them. We used fire. Well, the sun's light is energy also. Plants have a special ability, which they do through photosynthesis, to keep that electron at a really high energy level. It actually never falls back down. All right? So what happens is when we breathe in oxygen and we have that sugar, we can pull that electron away and actually steal the energy that the sun put in. And because oxygen is very electronegative, it pulls that electron, okay? So we call it the electron transport chain. So if you're taking AP Bio or plan on taking it, you'll learn all about that, okay? So now, finally, we're done with our review. Okay, notice we've spent a lot of time on ions and electronegativity, because now we're going to talk about ionic bonding, all right? So, ionic bonding creates compounds, all right? So we often say we have an ionic compound of something. So there are three major types of bonding. We've got ionic, covalent, and metallic. Ionic creates compounds, covalent creates molecules, metallic creates alloys. All right, so let's see if I can get a little pen here. All right, ionic, this is your compounds. All right, compounds. Covalent is molecules. Apologize for the scribble here. And metallic is alloys, like a metal alloy. All right, so we're going to talk about all of these things in just a minute. Okay. So, bonding basics. Ground rule for all bonding. All atoms want to be the happiest they can be and have an electron configuration that ends with or has a valence shell of something s2, something p6. For example, 2s2, 2p6, or 3s2, 3p6, or 4s2, etc. Okay? They really, really want to have 8 valence electrons, 2 plus 6. So ionic bonding. This is probably the most well understood type of bonding and the easiest to learn because it's really simple. The basics. When you have a positive and a negative that are near each other, they attract. Okay? So when we make a positive and a negative atom, we have an ion, and ions will attract each other. So when you get a positive ion and a negative ion, they attract. And that is an ionic bond, okay? It's really simple. It's just like magnets. If you get a positive and a negative magnet together, they stick. You get a positive and negative atom together, they stick. Okay? So again, when we look at predicting, okay, which will gain and which will lose, well, you have to look at the electronegativity. So ionic bonding, okay, occurs when the difference between the electronegativity of the atoms is greater than 1.7, okay? 1.7. So let me erase that just a little bit. All right. So 1.7, that's an important number. So for example, if we use the numbers we had earlier, if we have francium, which has an electronegativity of 0.8, and fluorine, which has an electronegativity of 4.0. Well, what's the difference between these? The difference is 3.2. Okay, so if I have a difference of 3.2, is that greater than 1.7? Yes, it is greater than 1.7. So will francium and fluorine form an ionic bond? Most definitely they will. See how we just worked through that and we were able to predict that fluorine and francium will react without ever actually doing a reaction. Okay, so how do we start? Simple. Let's write out the electron configuration for chlorine and sodium. All right, so you guys do it while I do it. Okay, so I know it's scribbly, but alright, we've got sodium 1s2, 2s2, 2p6, 3s1, chlorine 1s2, 2s2, 2p6, 3s2, 3p5. Simple enough. Alright, now it says to do the Lewis dot structure for them. Alright, so how many electrons does chlorine need to be happy? And how many electrons will our sodium need to be happy? Alright, so let's just erase all this so we can see what the heck we're doing. Okay, so let's look at it. Now, is chlorine more electronegative than sodium? Remember your trend. We're going to increase electronegativity that way. So if they're both on the same row, okay, or the same period, then yes, chlorine is more electronegative than sodium. So what happens? Alright, so here's an example of an ionic bond with our two elements. We did the configurations here and here, and we found that we had two valence electrons, so we drew our Lewis dot, and then we drew our other Lewis dot structure. Once those were completed, we figured out where the electrons would move with arrows, figured out the charge, and figured out how these would bond. Because calcium lost 2 electrons, we have no dots around it. Oxygen gained 2, so now we have 8 dots. Here's another visual, a different way to represent this using sodium and chlorine. Okay, so we've got our different energy shells here, different numbers of electrons on each shell based on how the orbitals are filled. Notice how sodium lost 1 electron and chlorine gained it. We always, when we bond stuff, we always want to try and be neutral. Okay, meaning the entire compound needs to be neutral. So what do you do with magnesium and oxygen? Well, it's pretty simple, right? You've got a +2 and a -2, so they cancel out. So what about magnesium, which has a +2, and chlorine, which has a -1? Well, it's pretty simple. You have to use 2 chlorines to cancel out the positive magnesium. So how do we know how to figure out, how many we need to cancel and stuff? Well, it's really quite simple. Let's take magnesium bromide as an example. First, put your elements side by side, like so, where the positive ion comes first. The cation is the positive one. Alright, so that comes first, so we've got magnesium on the left. Next, write the oxidation number for each ion. +2 for magnesium, -1 for bromine. Because magnesium is an alkali earth, it always has a +2. Because bromine is a halogen, it always has a -1. Crisscross them. Okay, so if I have a +2 and a -1, this 2 goes over here, this 1 goes over here, and as a result we get Mg1Br2. Now the 1 is not usually written because it's assumed to be there. So some new vocabulary for you to learn. Oxidation number is the same thing as saying charge. Cation is a ion with a positive charge. I think of cats because cats make me happy, so put a little smiley face. Alright, anion is an ion that is negative. So I always think of Anakin Skywalker. For those of you who aren't Star Wars nerds, Anakin Skywalker is the person who becomes Darth Vader and eventually wants to succeed and keep the Empire going and all of that. So he's not a very good person. Okay. So now how do we name ionic compounds? All right. Naming things with a fixed charge. So fixed means it only has one charge always. All right, very rarely is this rule ever broken. So these are alkali and alkali earth metals. Alkali always get +1, alkali earth always get +2, and that's because of their valence structure. So the non-metal in a compound ends in ITE. Here are a few examples. Calcium oxide. You don't say CaO or calcium oxygen. It just becomes calcium oxide. So see how we change the ending. Sodium iodide, barium chloride, sodium chloride. All right, and you'll learn where they break just by memorization and looking and seeing lots of these. Notice how the cation is always first, the anion is always second, and how all of my metals in this case are either alkali earth or alkali metals. But we do have some things with variable charge. For example, the transition metals, which means they have more than one charge, more than one oxidation number. For example, iron can be a +2 or a +3. So we're going to use Roman numerals to note which ones are which. All right, iron 3 chloride. See, we still change the ending, but we stick this Roman numeral 3 in here. Well, where did that come from? Well, chlorine. Chlorine is a halogen. Chlorine always has a -1 charge. I have 3 of them, which means I have 3 negatives, which means this iron, in order to become neutral, has to be a +3. A 3 in Roman numerals is 3 I's. Okay, iron 2 chloride, same thing. -1 charge. 2 times -1 is a -2, which means this has to be +2. So iron 2 chloride. For these last two, see if you can do it. All right, where did these 3 and the 4 come from? Why do you think that is? So take a second, pause the video, and work those out. Use the same logic as what's here. Now, properties of ionic compounds. This is if I want to use them in an experiment or use them to do something. What properties do they have so that I can do other reactions with them? First, they're soluble in water. Okay? If you take table salt, which is sodium chloride, you put it in water, it will dissolve. That means that it breaks apart. It goes back into its respective atoms. They have a high melting and boiling point. It's really, really, really hard to overcome a positive and negative attraction. It takes a lot of energy to do that. If you would like to use these to conduct electricity, like you want to make a battery, you cannot use a solid salt. It will not conduct electricity. Okay? You have to dissolve it first or melt it. Most commonly dissolve it. So if you want to make a battery, for example, then you need to first dissolve the salt so that you get the ions moving around. And those ions moving are what cause the electrical current. And finally, these are not molecules, they are compounds. All right, everybody will make a little slip every now and then and call them a molecule. That's okay, but just know they're not molecules. They're compounds. They are just 2 magnets stuck together. There is not a permanent bond between them. Here are some practice problems, okay? So if we're done with ions for now, we're going to come back and revisit them much later. But for now, all right, tell me, how are ionic bonds formed? What properties do ionic compounds have? Okay, write it out. If you don't know it, go back, look at it, rewatch the video. Okay, what's the proper name for FeO? All right, we don't call it FeO, so write it out. Also, what type of metal is iron? Is it going to be one with a fixed charge or a variable charge? Because that might change your name. And finally, what is the proper formula for an ionic compound between calcium and chlorine? All right, it's multiple choice. but you need to go figure it out. So what's going to be the charge here? What's the charge here? How do you make them neutral? All right. So that's it for ionic bonding. So I hope you learned something. We'll be doing lots of practice in class. So I'll see you next time.